these two chapters now, this Polynomial Congruences 1 and 2. So Polynomial Congruences 1, this chapter 6, dealt with the starting off case of linear congruences, so polynomials of degree 1. And we completely described the situation for those in our Theorem 6.3. It was a complete algorithmic description of what happens with linear congruences. How to decide if and when they do have solutions, and when they do have solutions, how to get a complete description of them modulo the original modulus n. Okay. So we did that in last week's lectures, maybe even the week before that. The other part of Polynomial Congruences 1 chapter was the Chinese remainder theorem, which allowed us to take a number of different congruence classes, modulo a set of moduli which are pairwise coprime. And if they are pairwise coprime, the theorem says that any collection of congruence classes like this always comes from a unique congruence class modulo the product of all the moduli. Okay. So we looked at the proof of that last time, and in the tutorials last week we worked on some example problems of those linear congruences in the Chinese remainder theorem. Okay, so we're going to go on now to chapter 2. Or any questions lingering for clarification on parts of chapter 6, or any queries? Okay. So into the second chapter then, Polynomial Congruences 2, and that is going to take all that, and it's what are we going to culminate in? We're going to culminate in describing the procedure for solving a general polynomial congruence modulo a general modulus, modulo n. Okay, we're going to use the material we've done in chapter 6 together with a few extra things from chapter 7 to describe that. Now the first step in it, a fair bit to get here, is a theorem due to Lagrange. And it concerns relating the degree of the polynomial to the number of solutions that it might have. Okay? Now, in our the initial examples we looked at, we saw that there was no simple link between the degree of a polynomial and the number of solutions that the congruence has. Okay? In contrast to the situation of polynomial equations over the complex numbers, where the polynomial has exactly, if the polynomial has degree n, then it has exactly n complex roots counted with multiplicity. There isn't such a simple direct link for polynomial congruences. However, there is such a one when we restrict to just considering a congruence modulo of a prime number. Then we have this theorem due to Lagrange, which again isn't an exact link, but it's as close as possible. So let's have a look at the statement of the result. It says if f is a polynomial of degree n, so that notation just the sum of ai times x to the power I. That's just notation that can represent a general polynomial. We're going to consider the polynomial congruence. So f of x congruent to 0 modulo p. So this is theorem 7.1, page 47, modulo p. Now, this notation here suggests that the degree of the polynomial is n, because it goes all the way up to x to the power n. However, when we're speaking modulo p, to ensure that it is genuinely of degree n, we have to insist that the top coefficient, an, is not congruent to 0 modulo p. Because if now p is a prime, so that means p does not divide an. Because the only way an could, the only way an could be congruent to 0 is if it was divisible by p. So when we have that condition there, that means that when you consider this polynomial modulo p, it is genuinely of degree n. Because if the top coefficient an, if it were a multiple of p, then the polynomial wouldn't really be of degree n modulo p, because the coefficient of x to the power n would be 0 modulo p, so it wouldn't really be of degree n. But if it is genuinely of degree n modulo p, then this theorem says that the polynomial has, the situation with equations is it has exactly n solutions of the complex numbers, but talking congruences, it's slightly different. We have to say it has at most n solutions. Most n solutions. So there's a little illustration of this that I was just doing just before I came here, which I'll just show you some. Oops. Just a few results. So here I just set up a polynomial, 7x squared plus 5x minus 10. And if we look at, in Sage, there's this solve mod command which solves the congruence. So 37 is a prime number. The polynomial f, we're solving it f of x equal to 0 modulo 37. It's a solve mod. So it reports two solutions. So you got two solutions, and the polynomial is of degree 2. Now, for most primes that you put in there, you will find two solutions. 7 and 12. What's another prime? 49. 49. No, 49 isn't prime. 49 is 7 squared. What's a close prime to that? 51. Is that prime? Yeah. No, it's 3 times 17. What's the next prime? 51, 53? Yeah, I think 53 is prime. Yeah. 28. So we seem to keep getting two solutions. But something funny does happen for some values. So if we just go, let's say, do all the primes between 2 and 100. So this little loop here, let's get rid of that line. So there's, I quickly ran through a loop. So this is all the primes p in between 2 and 100. We print p and print up the solutions of f of x congruent to 0 or modulo p. You see, most of the time we get, well, we have two solutions there, but sometimes we have no solutions. So there's no solution. See, the solutions should be in this pair of brackets here. So modulo 3, there's no solutions. Modulo 5. That's interesting. Modulo 5, there's only a single solution. Single solution, modulo 5. 7, well, the prime 7, well, that doesn't fall within the scope of the theorem, because really this thing isn't of degree 2 modulo 7. It's only of degree 1 modulo 7, because that coefficient is 0 modulo 7. But for all the primes after 7, see, we're either getting no solutions or two solutions. Except sometimes only for the prime 61, we're back to only one solution again. But we certainly never see 3 solutions or more solutions. So that's all the primes between 2 and 100. Extend it a bit, look a bit more, all the primes between 2 and 1,000. We only ever see no solutions or 2 solutions, and very occasionally for 61 and the prime 5, we just had single solutions. And single solutions might crop up again. That one there? No. So we certainly never see 3 solutions. So we can certainly see numerical evidence for that when we look at particular examples. Okay. So no solutions or 2 solutions. Okay, but how are we going to prove it? There's a little comment here before the proof. The proof's a particularly nice example of the use of induction together with proof by contradiction. Now, it appears long in the notes, but I've gone to kind of great lengths there to give a lot of explanation for it in the notes. Now, I thought for today, we won't simply just read through it, but I just kind of sketch out the main important steps of it on the overhead as we go. Okay? But I like it because it's, as it says, we see a couple of proof techniques combined. Induction, and within the induction proof, a kind of fairly non-trivial, nice, substantial proof by contradiction technique in there as well. Okay, so let's switch over to the visualizer, and we'll talk through the main elements of this. Any questions about the statement of the theorem, first of all, or what it means? So we've got our f of x, our polynomial. Oh, sorry, I'll use the notation of the theorem. So it's the sum of ai times x to the power I. Our I is going from 0 to n. And we're looking at f of x being congruent to 0. Sure that this is genuinely of degree n, we have that p does not divide an. So the top coefficient an x to the power n, it is there, modulo p. It isn't the case that the coefficient an is 0. So we're going to do induction on this. Now, it doesn't, the induction proofs we've seen before have always been proving things about integers, and you induct over the integers. Here we're proving things for every polynomial. So how do we do induction over polynomials? Well, what you want is some way to organize your polynomials so that they're indexed by integers in some way. And the most obvious one to use is that superscript and the summation there, the degree of the polynomial. Okay? So we perform induction. I'll try and not write too much on these pages because it is all in the proof in the notes. So we perform induction on the degree n of the polynomial. Well, we can certainly do that. So what we're going to do is prove a base case for degree 1 polynomials, called linear polynomials. That's a good thing. That's a good base case to use because from the previous chapter we already completely understand degree 1 polynomial congruences. So our base case for the induction will be those of degree 1. And then we'll do an induction step. So we'll assume that the theorem is true for everything of degree k. So for all polynomials of degree k, we'll assume the theorem is true. That's the induction assumption. And then from that assumption, we're going to try and prove that it must be true for everything of degree 1 more, everything of degree k plus 1. Okay. And somehow we need to make that deduction from the induction assumption. And that's where the proof by contradictions come in. We're going to make that deduction using the proof by contradiction. So the base case n equals 1. So i.e. you're considering something like f of x, which is just a1x plus a0 congruent to 0 modulo p. Now we completely understand these from the previous chapter. We do. This condition that p does not divide an means that p and a1 are co-prime. So it means there's an inverse to a1. There's an inverse to a1. You just multiply both sides by the inverse, and that will give you the solution. So the solution here, which we've already described in the previous chapter, so one solution modulo p. And the only justification we need for that is just to mark that a1 inverse exists since GCD of a1 and p is 1. Is that the base case? Does that prove that the theorem holds? Well, the theorem is saying that the degree of the polynomial is an upper bound of the number of solutions. If it's less than or equal to whatever the degree is, n solutions. Well, here's something of degree 1, and it only has one solution. So the theorem is true for degree 1 polynomials, okay? Because any x that solves it has to be congruent to this. So it's just a single congruence class modulo p. So one solution for degree n equals 1 polys. So the theorem is true. So the base case of our induction proof is true. Okay. I don't want to write too, as I say, I don't want to write too much on this because it's all so now we need to make the induction assumption. For the induction step. Well, how do we do that? We always assume we prove a base case, typically n equals 1, and we assume the result is true for n equals k, some intermediate value. So i.e. we assume for all f satisfying conditions, those conditions about the leading coefficient not being divisible by p, okay, that's understood. For all polynomials f of degree k, the result holds. Okay, so every polynomial of degree k, we're assuming it has at most k solutions. So that assumption is fixed in our minds, and then from that we want to deduce the statement for the next value of k. Okay. So we need to consider, we need to prove that it's true now for all polynomials satisfying the conditions of degree k plus 1. And this is where our, now, that's, when it's phrased like that, sounds like quite a task. Because we have to prove something for every possible polynomial of degree k plus 1 for a general k. Well, there's a lot of polynomials of degree k plus 1. If k is large, there's an awful lot of polynomials of degree k plus 1, an infinite family, parameterized by k plus 2 coefficients. So we're not going to attempt a kind of constructive direct proof. We're going to use a proof by contradiction technique. So that's the main move here. Proof by contradiction. So we assume what we're trying to prove is now false. And what we're trying to prove is this assumption here where n is replaced by k plus 1. We assume that that's false, and then we try and derive a contradiction from that. Now, what does it mean to say that the result is false? Well, the statement says for every polynomial, something is satisfied. So saying that's false, that means there must be at least one polynomial for which it's not satisfied. Yeah. When you're considering what would make a statement like this, for every polynomial f, something is true, what makes that false? It means that there exists at least one polynomial f for which it's not true. So to begin our proof by contradiction, we assume that there exists a polynomial g of degree n equals k plus 1, and that this polynomial has too many solutions. The result says these polynomials should only have the number of solutions at most the degree. So we need to, what we need to say about this assumed polynomial here is that it has too many solutions. So we assume there exists a polynomial g of degree n equals k plus 1 with too many solutions. So what would be too many solutions in this case? Well, it would be more solutions than k plus 1. But we'll be as conservative as possible with at least k plus 2 solutions. That's what we assume. This is, such a polynomial g is contradicting the theorem. That's exactly what we want, because we're starting a proof by contradiction. We're assuming such a G exists, and from that we're going to get a contradiction. Now, okay, we've done most of that in words. We need to start attaching variable names and notation. So what are we doing here? We're assuming there exists a polynomial G. So let's give some notation to that. So say G of X is, now I'll just use a different letter than the A just because. So this is what our G would look like. So this is just a general polynomial of degree k plus 1, going up to k plus 1. It's got coefficients b, just to differentiate it from the general f in the statement of the theorem. Now it must satisfy the conditions of the theorem. So b must not divide k plus 1. Sorry, p must not divide k plus 1. So it must be genuinely of degree k plus 1 modulo p. And it has too many solutions. And we want to give names to these solutions. We want to bring these solutions to hand. So let's introduce them. We'll indicate them as x0, x1, x2, etc. There's supposed to be k plus 2 of them, so the final one should be indexed k plus 1. So this has these solutions, i.e. G evaluated at x to the subscript I is congruent to 0 modulo p. Now let's be very clear on what's going on here. We haven't proved that such a G exists. We're assuming it exists. The only reason we're assuming it exists is to derive a contradiction from it, to prove it cannot exist. And then we'll know the theorem is true. And all of this is within a proof by induction. So we prove that it's true in the base case. We've made the induction assumption that it's true for every polynomial of degree k. Now we're introducing our contradictory polynomial of degree k plus 1. We want to get a contradiction from the existence of this G. Now what are we going to contradict? Where are we going to find our contradiction? Well, the place to find it is against this induction assumption we just made. So this induction assumption we just made, we're going to prove that this G contradicts that. So the structure of this proof takes a bit of digesting. This is the legitimate assumption we've made, because it's inside a proof by induction. We're supposed to make that assumption and then deduce it for the next level of polynomials. This second assumption here we've made is our proof by contradiction assumption, the assumption you make at the start of that. So from this G, from the existence of this G, we will contradict the assumption made at start. That's the induction assumption at the top of the screen there. And once we show that the existence of G contradicts the assumption star, that completes the inductive step. Because that proves that if you assume that star is true, it must be also true for the next set of polynomials of degree 1 higher. Because the existence of a polynomial of degree 1 higher which contradicts it is incompatible with the induction assumption. So i.e., we'll find an associated polynomial of degree k, so 1 degree less, with too many solutions. If it has too many solutions, it will contradict the assumption. So those are the steps and the logic I want to emphasize from this. The rest of it is some kind of algebraic, I won't say trickery, but just some algebraic manipulation of this G to perform this contradiction that we're talking about. So we want to reduce the degree. Find in G some other polynomial of degree k. And when you read through the rest of the stuff in the notes, that's what we go about doing. What we do is we consider a new polynomial called capital G. And capital G is formed from the little g, except we change the constant. So g of x, that's the general polynomial part. But we subtract the value that g has evaluated at the first solution. Remember, that's not the integer 0. That's an integer that's congruent to 0 modulo p. So this g of 0 is some multiple of p. So we're subtracting that from the polynomial little g. That gives us our slightly different polynomial capital G. So capital G is exactly the same as little g for every term except for the constant term. Except for the constant term. Now, you can see what we do then. Well, that's what g of x looks like there. Well, g of 0 looks exactly the same, except instead of x to the power I, it's x0 to the power I. So that's just introducing the notation we've got for the structure of the polynomial. Well, see, subtracting these two summations from each other, we can collapse that together into a single summation. Single summation, and this is bi into xi minus x naught I. So this is the summation of bi times x to the power I minus x naught. And x naught is some fixed number, remember now. X is the argument to the polynomial. X naught is some fixed number. It's one of the solutions of little g. So we got capital G like this. Now what do we notice here? You see, we're trying to step down the degree a little bit. Well, here we've got a difference of powers. See, the power is the same in each term. You've got a difference of powers of these two items, x and x naught. Well, we can always factorize such a difference of powers. We can always extract the factor x minus x naught itself out of that. And it'll leave behind some other polynomial. I'm not particularly interested in what it looks like, but some other polynomial the other polynomial it leaves behind is I'm running out of time here. Well, it's the other complementary factor. It's going to be x to the I minus 1 plus x to the I minus minus 2 x naught, and it goes all the way down to x naught to the I minus 1. The main move here is extracting this factor out and leaving behind some polynomial, which we write there as h of x. So h of x is this polynomial, the sum of these coefficients bi times these variable length polynomials in x. Well, they're counting down all the time. So the power on the x is decreasing, and the power on the x naught is increasing from 0 to 1 all the way up to I minus 1. What we're concentrating on is the existence of this h. Well, I slipped on a bit too long, but when we find this polynomial h, we examine this polynomial h. And what we find is this contradicts the assumption star, because it has too many solutions. This has solutions. This has solutions x1, x2, all the way up as far as xk plus 1. It's got k plus 1 solutions, but it's of degree k. Something of degree k that has k plus 1 solutions. So that contradicts the induction assumption, which we made at position star up above on the previous page. So therefore, the case of any polynomial little g is incompatible with the induction assumption that we made. So there can be no such ones. So that tells us every polynomial of degree k plus 1 has at most k plus 1 solutions. Because if anything has k plus 2 solutions, it immediately produces something which contradicts the induction assumption. So that completes the induction step. So you just wrap up the proof by induction then to prove the whole theorem.
That's right, John. That's right.
Okay, so what I recommend you do before, if I got I've got the lecture on Friday, number theory this week. So just have a read through the proof of that theorem, 7.1, and I'll take any queries about it, or we'll review it and just quickly look at the structure of it again at the beginning of Friday's lecture.
Yes,